In this video, I'm going to solve exercise 10, page 93. Consider a parallelogram ABCD. So we are given any parallelogram ABCD. And the first part, we want to plot the points M, N, P, and Q so that AM equals 3 over 2 AB, BN equals 3 over 2 BC, and so on. So let's start first with point M. Okay. So we want to have AM equal to 3 over 2 AB. So since we have vector AM a multiple of vector AB, this means that AM and AB have the same direction. Also, since 3 over 2 is positive, it means they have the same sense. So AM and AB, they share a common point A. They have the same direction and same sense, but the magnitude of AM is 1.5 or 3 over 2 times that of AB. So we look at vector AB. So this is vector AB. We want AM to be having the same direction, so they are collinear. The points AM and B are collinear. Same sense, so it should point in this way, and its magnitude should be 1.5 times the magnitude of AB. So let's look here at the AB that I drew here. Its magnitude is 4 units. So I multiply this by 3 over 2, I get 6 units. So the length of AM should be 6. Okay, so this means that AM should be the following vector. So AM, so M should be this point here. We do the same thing for the remaining points. So let's move to the next point. So this is M. The next point is N, such that BN equals 3 over 2 BC. So we have BN equal 3 over 2 BC. Similarly, we have the vector here BC. So since BN is a multiple of BC, then BN and BC have the same direction. 3 over 2 is positive, so they have the same sense, so N should point upward. And the length or magnitude of BN should be 1.5 times that of BC. So you measure the length of BC and multiply it by 1.5, and you draw the point N, which should be somewhere here. So in our case, N will be this point. Okay. Similarly, we continue with the third point. We have CP equals 3 over 2 CD. So this is CD, CP, so same direction, same sense, but the magnitude is 1.5 times this. This is 4 units. When you multiply it by 3 over 2 or 1.5, you get 6 units. So this is point P. And finally, we have point Q, defined by dq equals 3 over 2 dA. So this is vector dA. By the same argument, Q should be on this side, so it should be somewhere here, such that the length of dq is double that of 1.5 times that of dA. So this means that Q will be here. Part B. Find BM and DP in terms of AB. So let's start first with BM. We want to have BM in terms of AB. Notice here I have BM. To get AB, which is just minus BA, I can insert here letter A. So if I insert here letter A, I would get AB, which I want. Also, I would get AM, which is 3 over 2 AB. Okay, so first, if I insert here letter A, I would get BA, which is minus AB, and plus AM. This is what we want, because we want everything in terms of AB. So BA is simply minus AB, and AM is given to be 3 over 2 AB. Now, minus 1 plus 3 over 2 is 1 over 2. So this becomes 1 over 2 AB. Okay, so you treat vectors as you treat x, for example. If you have minus x plus 3 over 2x, you get 1 over 2x. So you treat it in the same manner. Now let's find the second vector. The second vector is dp. So here, of course, we applied Chase's rule. The second vector is dp. I want to write this in terms of AB. So I will go back to the given. What do I have concerning P, the new point P? Because we have A, B, C, D are the original points, and the added points are P, M, N, and Q. So what do I know about P? Where do I have P here? I only have P here in CP. Okay. So I think of inserting letter C. If I insert letter C, I will get DC plus CP. CP is already 3 over 2 CD. And remember, CD from the figure, CD is BA. So CD is BA, which is minus AB. And our goal is to write everything in terms of AB. So it would be a good idea to insert letter C using Chase's rule. So I will insert here C. So this becomes DC plus CP, also by Chase's. But DC is equal to AB, as we said, because ABCD is a parallelogram, so we've just seen it in the figure. And CP from the given, go back to the given, CP is this. So it's 3 over 2 CD. So it's 3 over 2 CD. And we've just seen from the figure, so again, I'll show you the figure. CD is what? CD is equal to BA vector. CD is equal to BA, which is at the same time minus AB. Okay, so I'll write it directly as minus AB. So minus 3 over 2 AB, since CD is equal to minus AB. And we simplify. So we get AB minus 3 over 2 AB. So 1 minus 3 over 2 is minus half. So it's minus half AB. Part C. Find each of the vectors MN and QP as a linear combination of AB and BC. Then deduce the nature of MNPQ. First, I want to define what linear combination means. So I've wrote this note. We say that a vector W is a linear combination of the two vectors U and V if W can be written as A times U plus B times V for some real numbers A and B. So for example, if W is equal, let's say, to 2U minus 1 over 3V, then W is written as a number times U plus a number times V. The first number A is 2 and the second number B is minus 1 over 3. Then I can say that W is a linear combination of U and V. Okay, so for example, if I have a vector, let's say CD equal 5CU plus 3UV, then this means that CD is a linear combination of the two vectors, and so on. Now back to the question, we want to write MN and QP as a linear combination of AB and BC. So let's start first with MN. So I want to write MN as a linear combination of AB and BC. So AB and BC. So I'll start with MN. Which letter should I insert here by applying Chase's rule to get things that are in terms of A, B, and BC? I have to look at the given first and at what I've proven in part B. So I have to use previous part. So for now, I have 6 equations to look at, and I want to choose which one is the most useful in our case. So first, I will go back to the original given. I'll check it here from part B. So the original given, we have AM equal 3 over 2AB, BM, CP, DQ, and we concluded two more things, that BM is half AB and DP is minus half AB. Okay, so our question is to find MN in terms of AB and BC. MN, so since I want to find MN, and for example, I have here from the previous part BM in terms of AB, okay? So I think of including or inserting letter B because I have BM and I want to find MN. So again, I'll go back to the question so that you see it. So I have MN, I want to find MN, and I know BM in terms of AB. So I think of inserting letter B here to get BM or MB, which is the opposite of BM. So if I insert this letter here, I would get MB plus BN. Now MB, I know it's minus BM, which we already found, and BN is also in the given. So BN is given to be 3 over 2 BC. Now, in the previous part, BM is half AB, so minus BM is minus half AB plus 3 over 2 BC. And now we're done because we wrote MN as a number times AB plus a number times BC, so it means we wrote MN as a linear combination of AB and BC. Of course, this is not the only way possible. For example, let's say someone did not pay attention that we found BM in part B and he was just looking at the given in part A. He could have thought of inserting letter A here. For example, we get MA plus AM. MA, we know it in terms of AB because we know AM from the given, but we remain with AN. We look at the given in part A. There is no AN given in part A, but there is BN. So for AN, we insert letter B. So we get AB plus BN. It would take more time, but it is also a correct method and it gives the same result. But in this question, to make it easier for us, they gave us part B as a step, a moving step between the two parts A and C. Now let's consider the second one. We want to find QP in terms of AB and BC. So QP. In terms of AB or as a linear combination of AB and BC. So which letter should we insert first? Of course, these are by Chase's. So we should write here Chase's rule. And let's think now what we should insert. So if I look at the previous part B, okay, I showed that DP is minus half AB. So DP, I have D with P. So I think of inserting letter D here to get DP because I have DP in terms of AB. So I will insert here letter D to get QD plus DP. Now, QD from the given, I have DQ. So QD is minus DQ, which is minus 3 over 2 dA. And dP from the previous part, it's equal to minus half AB. Now, dA from the figure is what? dA is equal to vector CB. So dA is equal to vector CB. So I will replace dA by CB because my goal is to reach something in terms of AB and BC only. So this is CB. Now, minus 3 over 2 CB is the same as 3 over 2 BC. So we get 3 over 2 BC minus half AB. So we were able to write the vector QP as a linear combination of AB, so it's a number times AB, which is minus half AB, plus a number, which is 3 over 2 times BC. So 3 over 2 BC. The second part of the question is deduce the nature of MNPQ. Notice here that we have QP equal to minus half AB plus 3 over 2 BC. And also MN equals minus half AB plus 3 over 2 BC. So we can notice that MN is equal to QP. So let's write this. MN is equal to QP. And we have seen before in the explanation videos that if MN, P, and Q are non-collinear points, and if MN, so I'll draw a sketch here, MN is equal to QP, then this means that quadrilateral MNPQ is a parallelogram. Okay, so in this case we have MN equal to QP, and also we have that MN, P, and Q are non-collinear points. So thus we can conclude that MNPQ is a par. Okay, so pay attention here. MN equal QP does not mean MNQP is a parm. It means MNPQ is a parm. So always draw a sketch if you don't have a figure. Now here, there was no need for this sketch because we already have the figure. So we can look at this figure. Notice we have MNPQ in a circular form. MNPQ is a parallelogram.